Hello, I'm Anthony Lomax, and I'm going to present our paper, High Precision Earthquake Location Using Source-Specific Station Terms and Inter-Event Waveform Similarity, recently published in JGR Solid Earth. Earthquake location is fundamental for earthquake response and seismological study. Stations and seismograms record seismic events. Some questions we want to answer are, where are the events located? What faults and earthquake hazard do the events define? But there are difficulties in answering these questions. One problem is error and outliers in the arrival time data we use to locate earthquakes. Another problem is the simplified and erroneous seismic velocity models we use for locating earthquakes. We know from geology that the Earth is highly complex. But for practical reasons, when locating earthquakes, we often use a highly simplified model. To address these problems and better locate earthquakes, I will present NonLinLoc-SSST-coherence, a method for high-precision, absolute timing earthquake location. This procedure is based on the probabilistic global search NonLinLoc location algorithm. One of its features is that it's very robust to model and arrival time error. It also produces locations as a probabilistic cloud, a location PDF. We extend NonLinLoc in two ways. The first is NonLinLoc-SSST, multi-scale, source-specific station travel time corrections. These corrections greatly reduce velocity model error and improve large to small scale precision in the locations. The second improvement is NonLinLoc-coherence, which performs a stack of location PDFs for nearby events defined by their waveform similarity. This procedure greatly reduces arrival time error and improves fine-scale precision of the locations. To illustrate the performance of NonLinLoc-SSST-coherence, we will look at relocations of Mendocino, Northern California seismicity. Routine earthquake location catalogs usually show diffuse seismicity due to the use of linearized location algorithms, basic velocity models, and simplified or no station corrections. Probabilistic, robust, NonLinLoc locations without station corrections show slightly more organized features in the seismicity. NonLinLoc location with the addition of 3D SSST travel time corrections greatly sharpens clustering and linear features in the seismicity, especially on the intermediate scales. NonLinLoc-SSST, with the addition of waveform coherence location, further sharpens clustering and linear features in the seismicity on the finest scales. Widely used waveform cross-correlation differential timing location methods, such as HypoDD, give very high precision on the finest scales. The NonLinLoc-SSST-coherence seismicity is similar to that of HypoDD onshore, to the east, but shows sharper features offshore, to the west, where station coverage is lacking. For another illustration of the performance of NonLinLoc-SSST-coherence, we consider relocation of Parkfield, California seismicity. The multi-scale precision of NonLinLoc-SSST-coherence relocations suggest a different geometry for the San Andreas Fault at seismogenic depth than do differential timing HypoDD relocations. The HypoDD relocations show a curved and segmented fault around Parkfield. In contrast, the NonLinLoc-SSST-coherence relocations define a planar, near-vertical fault in this area. In summary, NonLinLoc-SSST-coherence combines source-specific station terms and waveform similarity to achieve multi-scale high-precision earthquake location. NonLinLoc-SSST-coherence approaches the precision of differential timing relative location methods and can give improved results when station coverage is poor. Multi-scale high-precision earthquake location can image new features and geometrical patterns in seismicity and faulting. Thank you very much for your attention.